Hi students. So today we start optimization tutorial 9. Today we are going to discuss a method known as quadratic interpolation, and this is a method which is quite popular in one-dimensional search. So after you have found the search direction, you essentially need to calculate the step size by doing line search, and quadratic interpolation is a method which lets you do this. I'm Dr. Ganguly. Now today we are going to do a problem involving this method. So remember there is a lecture 9 on the quadratic method. You can check out the lecture in a separate video. I am going to leave it in the description box and in the end screen. But today we are going to look at how to solve a specific problem using this method. First we are going to solve this problem by hand, that is using calculator, and then we are going to write a Python code to solve this problem. So essentially at the end of this video, you will know all about this method and then you can use it to solve optimization problems. You should also remember that the Python code developed in these tutorials can be used as kind of projects which you can actually say that you have done in case you are preparing for any job out there. So let us start with a very basic warm-up question first, which motivates this method. Let us try to find the minimum point of this quadratic function. Now to find the minimum point of a quadratic function, we can simply set the derivative to 0, and if we do that, we get this value alpha star is 1 for this particular function in red. Then the next stage we need to do is we need to get the second derivative, and the second derivative, if it is positive, if it's greater than 0, then we have reached a minimum point. Remember, the necessary condition only tells us that this is a candidate minimum point. It could be a minimum, it could be a maximum, it could be a saddle point. But in case the second derivative is positive, then we know it is a minimum point. Now, of course, we can see why quadratics are very attractive, because if I can fit a quadratic to a function, then I can find the minimum of the quadratic, and hopefully it's going to be pretty close to the minimum value of the function. So that brings us to question number 2, which is find the quadratic fit for this function given here. This is the same function which we have been using throughout the one-dimensional search part of this tutorial series. Now here, this function, if we want to do a quadratic fit, we need to get 3 points, and essentially we have these 3 points here given by these values of alpha q, and corresponding to these 3 points, I also have the function value at these 3 points. So essentially, if we have 3 points and the function values at these 3 points, then we can try to fit a quadratic through this function. So in the lecture, I have given you these formulas. I am giving out these formulas again here. If you want to see the derivation, refer to optimization lecture 9. So essentially, if we have this function f and we want to find the quadratic fit q, then I need to find the coefficients a0, a1 and a2 for this quadratic. And to do that, I need to calculate these values here, a2, a1 and a0. Now you can see a2 can be calculated if I have all these values here. Remember here that we are using the nomenclature such that alpha L and alpha U are the lower and the upper bounds on this particular value, and I is some point somewhere between these two extreme values. So if we know these 3 points, then essentially we can find a2 from this calculation here. Now once we have obtained a2, we can obtain a1. Remember, a1 also depends on a2, and we can obtain a0. A0 depends on a1 and a2 also. So one of the things, of course, which you will realize here by looking at these formulas is that there is this term in the denominator at places which can become very small. So you should ensure that, of course, these terms are sufficiently far so that you are not dividing by some very small number. Remember, whenever you are doing computational math, then these kind of things like division by small numbers can become problematic. So let us now apply these particular formulas to the given problem. So like I mentioned before, I have the 3 points given here, and I have the function values for these 3 points. So let's start with calculating a2. I use this formula here. I plug in all the numbers from this table, and then after some simplification which I have done using my calculator, I obtain the value a2 is 1.375541. Now why I'm doing all this by hand is that I'm going to use these numbers to actually check out the output of my Python code. So that's something always useful to do in case you want to check out the veracity of your computer program. Now let's come to the next point, which is a1. So we have calculated a2 here. Now in case of a1 we require a2, and then we require all these values of the function, and we also require the value of the point. So once I do all those substitutions using the numbers given in the table here, these numbers in red, I obtain the value of A1 to be minus 0.969785. So now I have obtained A2 and A1, two of the coefficients in this particular quadratic fit. So I'm left with only A0, and the formula for A0 is given here. So to calculate A0, I need A1 and A2. I have A1 and A2, and then I need the function values and the value of these numbers at some point. I put in all those numbers here, and then I get A0 as 0.99781. So you can clearly see that, for example, if alpha L is 0.1309, I'm putting that value here and here. And of course, if F value at alpha L is 0.89444, then I am putting that value here. So now we have obtained A0, A1, and A2. So we can write the quadratic fit as follows. So you see the function in red, that is the actual function we have, and the function in green, that is the approximation using the quadratic. So you can see if I plot these two functions, which I have done here in Microsoft Excel, I essentially have the function here in red and I have the quadratic fit here. Now this function is smooth and well behaved, so the quadratic fit is actually working out quite well. And you can also see that the minimum point of the quadratic fit is quite close to the minimum point of the actual function. Now this may or may not be the case depending on the problem concerned. If you are dealing with very nonlinear functions, then this may not happen. But what may happen is that in a close neighborhood of the minimum point, your function may still behave in a quadratic manner. So that's something which happens for most mathematical functions, at least most functions which typically are present in practical engineering and physical problems. So that's something which we can use. Now let's come to question number 3, and this question essentially tells you to find the quadratic fit again, but this time you need to write Python code for this problem, and essentially these three numbers are given here. Now some of you may remember this set of numbers from the golden section search tutorial 8. So in that tutorial I used the value delta is 0.05, and then we essentially move forward in the design space, and then we bracketed the minimum between these 3 points. So what happens there is that the function value reduces, like you see here, between q is 0, 1, 2, and then it goes up at q is 3. So essentially by doing this, we were able to bracket the minimum point between 0.1309 and 0.473586. So whenever you are using this kind of quadratic interval method, quadratic search method, you need to use some different method to bracket the minimum. Golden section search is probably one of the best methods. So let us assume we have bracketed the minimum. So we have these 3 points here. So I have written this very simple function here. So this is the function quadratic. It takes in AL, AI, and AU. So I am using this nomenclature here, and then it calculates the function values, and then it does all the mathematics to get A2, A1, and A0. Now remember, the function is something like this, so it's expressed as x square plus e to the power minus x. I also have to import numpy because numpy is required for calculating exponentials. And what happens is that this particular function f of x, this is used in the quadratic function, and then I basically do all these calculations, and at the end of it, this quadratic function returns a0, a1, and a2. So I can simply write A0, A1 and A2 equals quadratic, and I can put the values of AL, AI and AU, and those are the three values which you have seen before, obtained from golden section search in the previous tutorial. And then I print these values out and I get these three numbers here. Now if you go back and check the previous derivation or solution which I did by hand, I used my calculator there, you will find that these numbers are pretty much the same as the numbers I obtained at that time. So essentially it is much easier to do this in this form here, which I have done. Now remember, I am not using any kind of safeguard here in all these divisions and multiplications, because I am just writing a code which fits in the slide very well, and therefore we can see it properly. Now if you are writing a real program for actual usage, then you should have some built-in safeguard so that the numbers AU and AL don't become very close, the numbers AI and AL don't become very close, and so on. So again, you can have various checks into the computer program, built into the computer program, which can exit the situations if there is a problem instead of simply crashing. So that's something important in numerical solutions. So let's now turn to the main problem, which is to bracket the minimum of this function. We will start with golden section search with delta is 0.05, and then we will use the quadratic search to find the minimum point. So this is actually what you want to do in the quadratic search method, and we are going to try to do this. So first we are going to do this by hand, and then we are going to do it by Python. So let's first do it by hand to figure out how this method works. So we start with the 3 points here, alpha L, alpha I, alpha U. These are in red, and I can immediately calculate I and alpha star. So alpha star comes out to be 0.3022, which is still quite far from the actual alpha star, which is 0.3517. Remember, the problem can be solved completely using mathematical techniques, which I have done in tutorial 3. That's the optimality criteria tutorial, where we obtained the solution in terms of the Lambert W function. So let us immediately fit the quadratic fit through it. The quadratic fit we know because we have derived it before. So what would of course happen is that if I were to get this quadratic fit, I can immediately figure out the value of alpha bar, or the minimum corresponding to this quadratic fit, and that alpha bar comes to 0.3525. Now we can simply put this in a code. We are going to do this later. So essentially alpha bar is going to be minus a1 by 2a2. Now, if you are interested in details about the theory, the derivations, make sure that you look at the tutorial on quadratic method, or rather the lecture on quadratic method. And of course, we know the exact solution is 0.3517, and in fact alpha bar comes to 0.3525. So in this particular problem, the solution is pretty good as far as we are getting the quadratic fit to be quite a good fit at this point. Now this can happen in many situations, but there may be situations where this doesn't happen. So now what we do is we have these 3 points, of course, alpha L, alpha U, alpha I, and now we have a new point which is obtained as the solution obtained by minimizing the quadratic fit. So that is alpha bar is 0.3525. So if I make all these points in a number line, then I clearly get these 4 points here. And now what I can do is I can calculate the function value at these 4 points. So this new point is alpha bar, that is 0.3525. Now this diagram is not to scale, but it does tell you how things can happen. You could get this green point on the right hand side, or you can get it on the left hand side depending on your function concerned, your fit concerned. So once I have obtained these function values, then we can bring in some aspect about comparing the values and so on. So now we have got 4 points. We have got alpha L, we have alpha U, alpha I, and now we have the point alpha bar also, which I have given in green, which is the minimum for the quadratic fit, and we have the 4 function values also. Now we need to check a variety of cases. For example, we can check in this particular case that alpha I is less than alpha bar. You can see that clearly here, because alpha I is 0.26 and alpha bar is 0.35. So this is true. Similarly, we have to check the values of the function at these points. So essentially, if we check these functions, we see that the value of f at alpha I is greater than the value at alpha bar. So these conditions being satisfied, we have certain things which we need to do. We can essentially reduce the bracket to alpha I and alpha u. Therefore, what we will do is that we will set alpha L1 is alpha I1 is alpha bar, and alpha u1 is alpha u. So you see what's happening here. The lower bound has become alpha I, the maximum bound has become alpha u, and the point between these two has become alpha bar. Now there are four possible cases which you can consider here. I have given these in the optimization lecture 9. Take a look at that to understand these four cases. And then what happens is that the minimum has been bracketed between 0.2618 and 0.4735, and now we set these particular values as alpha L1, alpha I1, alpha U1. So we put the superscripts 1 here to clearly bring out the fact that these are the next values for the problem. Now let us look at these three values here. We have obtained these three values, and we can immediately obtain I1, and we can also obtain alpha star. So we see that alpha star comes out to 0.3676, and this is pretty close to, of course, the actual minimum value of 0.3517, but still not so close. So we are going to look at that further. Now what's happening here can be seen graphically if you look at this number line. So essentially we had these 3 points. We found this point alpha bar using the quadratic fit, and then we compared the values of the function at all these 4 points and the fact that whether alpha I is to the left or right of alpha bar, and then we were able to discard this portion here, and so the bracket became only this much. So now I have 3 points, and alpha bar has become the new point here. Now of course these figures are not to scale, but they show you how this quadratic method works. Every time you are going to find this kind of value, and then you are going to reduce this particular bracket. So now what we can do is that we can clearly drop that one subscript which we were carrying along, and therefore we can now say alpha L is 0.2618, alpha U is 0.4735, and alpha I is 0.3525. Now you see that this becomes like a new round of this method, and you can proceed further. You have I is 0.2118 and alpha star is 0.3676. Now all these numbers are going to be useful when we look at the Python code in the next problem. And when we do the Python programming, we can print out the various values, and we can see that these numbers will get printed out at least in the first round of the Python code run. So this is a way to check out the correctness of the implementation of the algorithm. So at this point, we are ready to write a Python code to solve this problem. So first we are going to find 3 points using the golden section search, and then test the code with this function we have been using for a long time. So let us first start with the main Python code. So again, I bring in NumPy, and then what I do is that I bring in a function bracket minimum. This is actually going to use golden section to bracket the minimum to 3 points AL, AI, and AU. Then I'm going to do the quadratic fit, and I'm going to obtain A bar, which is the minimum of the quadratic fit. Then I'm going to do a quadratic search, and this is going to go through many times. In this case, I have given 10 times here, and it's going to continue this process till the value of I becomes less than this tolerance 0.001. So that's the way this method is going to work. So let us start with the point of bracketing the minimum first. So again, we have a simple function to define the function, that is x squared plus e to the power minus x. We then have this bracket minimum function here. So again, this essentially calculates these points. Remember the golden section method, and what it does is that it brackets it to 3 points, and so once it has bracketed it, it returns those three numbers, and then it breaks out of this for loop here. So essentially this function bracket minimum is simply returning to us AL, AI, and AU. Now, once I get this AL, AI, and AU, I call this quadratic function, and this quadratic function is going to return a bar or the minimum of this quadratic. So it's going to essentially take the function values at these 3 points, and then it's going to calculate A1, A2, and A0, which are the coefficients for the quadratic, and then I'm going to get the minimum point of the quadratic, which is minus A1 by 2A2. So essentially A bar is what I'm interested in, and quadratic returns A bar to me. Now the main body of the code is here. So let us do this. And in this thing, what happens is that you basically keep doing this many times. I have just put a number 10 here because it converges quite fast. You can put a larger number here also. And essentially what happens is that I have an important function here which essentially keeps calculating the new values of AL, AI, and AU with the superscripts 1 by using the old values of AL, AI, AU, and A bar. Remember, those values are coming into this function here, and each time it calculates the new value of A star, it calculates the new value of I1, and then it removes the superscript ones, and then it calculates A bar again by using AL, AI, and AU. Remember, A bar is the minimum of the quadratic, and then it prints out the values of the minimum point A star, and I have used the round function to round these to 4 decimal places because it was coming out to too many decimal places in some of my previous Python codes. And if I is less than tolerance, remember tolerance was 0.001, then you essentially break out of this for loop. So this is how you get out of this loop. Now the important point here is this function I have defined called new interval, and that function is the main function here which we are going to look at next. So that's the function here, and this is the function where all the logic is built into for this method. So essentially we have the points AL, AI, AU, and A bar, and then I have the function values here. Now you remember there are two possible conditions: AI is less than A bar or not, and depending on that it will go into these two loops. And there are also the possibilities that if AI is less than if A bar or not, so depending on that it does these two sets of assignments here. Now take a careful look at the optimization lecture 9, the quadratic search, to see all these four conditions. In that lecture I have made graphs of all these four conditions to show that why your minimum point actually then is bracketed within these particular situations. So for example, in this case the minimum is getting bracketed between AL, A bar, and I. Similarly, it's going on here. So there is a lower bound, the upper bound, and there is a midpoint here. So all these four conditions are there. And at the end of this function simply returns AL1, AI1, and AU1. Now Python has this nice feature that you are able to return, for example, a tuple of numbers. And then when you call this function, when you invoke this function, you simply get this tuple. So we have done enough programming. Let us now run it. So here I have run this here. I have done all this in Google Colab. So if you are interested, you can go to Google Colab and use it. I think it basically uses the same thing as Jupyter Notebook, but it is an online system, so you don't have to download too many things. Of course, if you are somebody who has already downloaded and has Jupyter set up on your computer, you can do it there. So here you see the minimum first got bracketed between these 3 points. So that's coming from the golden section search. That was the point where I had minimum at 0.3022 and 0.3427. Then we proceed forward here, and at the end of 7 steps I get minimum is 3517, and I value becomes very small here. You see the I value keeps progressively decreasing. Now at least in this particular problem I see that the problem got somehow stuck at 0.3517 for some time, but then at the end it was capable of converging. So this is something which can happen in this method, because what may happen is that you may get one point which is pretty close to the next point here, and you are very close to the minimum point, so it is essentially moving between these points, but generally it will work out well for most functions. Now I would say that in many cases golden section of course is more of a guaranteed method, but this method is also sometimes good. Sometimes you may just get a good solution in a step or two in this method and just stop it right there, because golden section itself would have converged the problem to you quite well, which we have seen here. And so what happens is that the quadratic which you fit at this point is actually pretty good. So what you are seeing here is that the kind of minimum you are getting here, like 0.36, is not too bad actually. And here finally, of course, we did converge. So let us make some remarks at the end of this tutorial. You saw that we looked at the quadratic method, and this method is very important because while we have demonstrated it for a quadratic function, you could easily extrapolate it for a cubic function, and then that method would be even more powerful. So actually many commercial codes may use a cubic function here, and you can also experiment with that. Now Python code is of course very useful to implement these methods. You can learn Python by doing these kind of problems. So again, I would encourage students to use these Python codes as a kind of tutorial to learn Python itself. So you need to get beyond very simple problems like solving factorial n and solving problems such as x plus 2 and so on, and do some real problem. Then these methods are going to be very useful. It's a very efficient method, but it is also prone to ill conditioning, which we saw. And the ill conditioning can happen because the points may be very similar. There are divisions taking place. The divisions may be by small numbers and so on. So one of the solutions is to use hybrid methods. So you could, for example, sometime use golden section. You could sometime use the quadratic fit, and you could keep changing these methods depending on the scenario concerned. So many hybrid methods are of course possible, which can make your life better. Again, that is an area of research. If you are doing some bachelor degree project or even master's degree project, you can probably figure out some research problem by combining these methods and figuring out some good way to solve this problem. So I'm going to stop this tutorial today. Again, make it a point to look at optimization lecture 9 quadratic search. Also make it a point to see the optimization playlist videos every now and then when you have free time. Maybe you are watching Netflix, you could spend that time better watching the optimization playlist. And of course, if you feel you need more strength in math, look at the Math Mania playlist on my channel. And I will see you next on the optimization tutorial 10, where I'm going to look at Armijo's rule, which is actually an inexact line search. So till now what we were doing is we were trying to solve the problem exactly, get exact values for line search, but then there are methods which give you a rough solution to the problem, which may also be often useful. They may be useful, for example, in machine learning.